So I can say I played sport. It's recognized by the Illinois High School Sports Association.
But I can't play modern because my bank is out of the state.
That's the quiz. The quiz.
I'm doing MIPS or?
Hey,
We need a VISC.
I think he was exhausted.
let's get started.
Process that you guys went with, isn't it?
Hey, let's get started. Happy Thursday. Welcome back to Probability and Signal Analysis class. So last class, we talked about some course logistics, objections and grading, some information about assignments, exam. What we're going to do today, we're going to start about real probability. And we're going to start from sample space, events, and then go for how we can define probability as a kind of math, like algebra or other type of, math. We're going to talk about probability axioms or rules that we need to consider to make a probability similar to other type of math. We're going to talk about those. So we start with sample space, events, outcomes, Kolmogorov axioms. Kolmogorov is a Russian mathematician that first time actually introduced these axioms for probability to make that as like a type of math. And conditional probability. And if we get time, we can go for multiplication or chain rule. That is the basic. Actually, these two last one are the basic of artificial intelligence today. Conditional probability and multiplication or chain rule. We're going to talk about those as much as we can. But today is just basic. We're not going to go very deep. So first, sample space. Omega sample space. For about 2,000 years, we will look at the probability like this that I'm talking at the beginning of the class. So we considered, okay, so we have a set of outcomes when you do a random experiment. Like, for example, gambling is kind of random experiment that you are doing. So it has some outcomes. And if we consider all possible outcomes, that's called sample space. Like, for example, if you are tossing a coin, so that's kind of by chance can come head or tail. So the head and tail are all possible outcomes that can happen. So that's called sample space. So sample space is like everything that can happen in that experiment that we have. For example, rolling a die, because a die has 6 sides, and each side has one number. So the outcome going to be one of 1, 2, 3, 4, and 6. Okay, if I can draw here. So normally a die look like that. You have some numbers in this. And when you roll it, one of those okay, we are imagining that the die is a normal die, so it's always stay in a position that one of the numbers can be, read. Anyway, the sample space is all possible outcomes that happening for rolling a die. So it's 1, 2, or 6. But sometimes this sample space is not a digit. It can be a real number. Like, for example, in that example, when you have a thermostat that you are reading the temperature, that's also random. Why is random? Because it's not certain. The sensor is not 100% correct. It has some tolerance. That's why it's random. But the sample space is a real number. It can be a real number. Sometimes sample space is the finite numbers, like, for example, 1, 2, 3 to 6. Sometimes is not finite, like is just a number 1, 2 to infinity. This also can happen. So we're going to talk about those also today. So that is the sample space. So in general, sample space is all possible outcome of random experiment. We have a random experiment, and whatever happening, we call that omega or sample space, like in the overall. All possible situation that can happen. Let's do example for robotics. Imagine we have a robot that moving in actually grid space. Grid space is like a pixels space. When you have, for example, a space like that, and the robot is, for example, here, but the position of the robot, it depends on these pixels. We call them grid. So that's a very simple situation that we consider robot position. For example, here is 0 to 100, or 1 to 100, maybe, 1 to 100, 1 to 100. So this is grid. So in this space, robot can be in any of these positions. For example, here, of course, this is not 100, but for example, you are imagining this is like some between these more grids. So for example, here, imagine is, I don't know, 50, and here is, for example, 20. So right now is in this position. So it's two-dimensional. So sample space can be also two-dimensional. In this case, we can say sample space is x and y when x and y belongs to this set, because each of these points can be between 1 and 100. So for example, in this case, A, the position of the robot is 20, or maybe 50 is x and y. We consider this x and that y. So it's 50 and 20, for example. This is x, and this is y. So that's one of the outcome. A is one of the outcome that's happening. So all of the outcomes is this, sample space. So sample space showing all the outcomes. If we just consider one of them, that's called events. That's we're going to talk next slide. Any question? Yes?
The temperature reading, is that because we don't care that there's a lower bound because it's uncountably infinite?
Sorry, what?
Because like with temperature, don't you have
temperature?
A lower bound of 0 Kelvin, technically?
Yes. Yes.
It was do we not include that in our sample space?
Yeah, we didn't include that in that example, but we can include that, yes. But we just wanted to mention that this sample space can be a real number.
Okay.
Continuous number, yes. Yes, that's true, yes, you're right. We can consider some bandwidth, of course. That's correct, very good question. Very precise. So anything about this robot position example? But this is also can be continuous. Later on, we can see how we can define the position of the robot, because in reality, it is continuous. It's not certain. You don't have grid word. Maybe in the game, yes. But in reality, everything is continuous, you know. Even digital world is kind of simulation of continuous world. Okay, so this is sample space. If we consider one of the outcome, another example is a packet transmission. When you have a network, you are sending and receiving information. In networks, you are sending and receiving information by packets. Packets are like a bunch of information that you are sending in seconds or each time slice. So in this case, that is also probabilistic, because sometimes packet can get lost. So receiving a packet also can model as a, let I erase this, sample space. So the sample space in this case is success or failure. If you send a packet, you can receive it properly. It's called success or failure. So this is, but we can have more. It's just example. So, and so many other applications, you can define it as a sample space, events, and outcomes. What is event? Event is a subset of sample space. A subset of sample space. In that example of robotics, the position of the robot was just one of those grids, X and Y. So that's just one event that can happen. So for example, in rolling a die, rolling an event die can be one event. So one event can be like E246. So you have again a die. It has numbers on it. And you roll that. So for example, you want to see what is the probability of being even. Or what is the probability of being odd? The number become 1, 3, and 5, for example. Still, we are not talking about probability. I shouldn't bring that up, because still we are in how many years ago? Let's see. Before 1933, because after 1933, we defined to have a kind of math called probabilistic or probability, or stochastic processes. All the probability come after that year. Before that, we just consider probability as an event and this that using for gambling and this kind of stuff, or physics, but we didn't consider that as a math, because math always is certain. We were thinking, okay, math needs to be certain. How we can have a math that is not certain? Okay, so another example of the event is, for example, getting head when you are tossing a coin. When you are tossing a coin, we want to. One of the event is to just head coming, and the other one is tail for sure. That's called event. So the event is a subset. So we have a set, we have a subset, and if we look at that more precisely, we can see, oh, so much similarities between set algebra and probability. Because we said sample space is a set of all outcomes. Event is a subset. Again, subset is also set. So we are kind of find some similarities between actually set algebra. Set algebra is a branch of math algebra with probability. So this can give us some ideas, you know. You had set algebra in math before, yes? You know set, subset, yeah? I think so, yeah. Like Gantt chart, for example. Do you remember this? We consider this is all universal set. You remember that? We consider all universal set and said, okay, this is the set of A. This is set of B, for example. And this is, for example, A and B. This was set theory or theorem or set algebra. We had this before in math. And we can define not A, for example. So if you remember, or A complement, this we also had, for example, this is A complement. When I said A complement means the area that is not A. Something like that. This is a Gantt chart. It's called Gantt chart. It's the name of the guy that invented this method. It can be used a lot. Even in Boolean algebra, you use that. You remember? Like De Morgan law is also based off that. You can write, for example, A and B complement is A complement or B complement. This is a De Morgan law. So we had that in Boolean algebra, in set theorem. They are all same. So here we also can see some similarities between set algebra and probability. Okay, I just wanted to remind you this stuff. It's good for visualization. Sometimes when you visualize something, you can learn it easier. Okay. So let's erase this. Any question about this before I fill it up? Okay. We have some special events, like, for example, impossible event. When one event not possible to happen, that's called actually impossible. For example, that example of the robot is in a grid world. The robot cannot be in two different grids at the same time, simultaneously. Like be in point, like robot is in two different grids simultaneously. Okay, this is something that is not possible. So we call that impossible event. Another special event that we have is certain event. Sometimes event is certain, like 100% that happen. For example, again, in that example of the robot, we can say, okay, robot is somewhere in the grid or somewhere in the map. So this is always happening. So the probability of that, again, I still doesn't want to talk about this part. We're going to talk about that next slide. But this is always 1. So it's 100% in that case. Like robot is somewhere. In the map. Still, we need to have some information that the robot exists. If you want to talk about that part, first we need to say, okay, there is a robot in the map, and then we can talk about robot is somewhere in the map. So that's a certain event. Okay, and normal math is certain, like linear algebra is a certain. Or geometry is mostly certain things, Okay, so that's certain event. Another event that we have is actually singleton event, when just one outcome happened. When just one happened, again in robotics can be, for example, robot in a grid world is at, for example, x is 5 and y is 10, for example. One position. That's one example of singleton event. Okay, so that's just definition. Some a special kind of definitions, impossible, certain, because we use certain a lot. We sometimes saying, okay, this is certain. This means 100% true. We don't have uncertainty on it. Uncertainty against of certain. Anyway, and when just one outcome, singleton, I haven't used that much I don't know, but they just put name on it. But empty set, yes. Empty set happen a lot. Okay, so this was before 1900. After that, they were thinking, okay, because of application of probability, and we can see that everywhere, why we don't bring that up as a math? Why we assign numbers to that? Before that, we didn't consider number. As you can see, there is events. Events is tail and head, or those numbers that we were talking are the numbers in a die. After that, we decided to talk about these probabilities as a number and make it like a math. So the first guy that did that actually was Kolmogorov, Andrei Kolmogorov, that I can say changed all the world with that, with considering actually some rules for probability. We call that axioms of probability. And after that, we considered probability as a type of math. Becomes combined with other maths in the same level as those. So in that case, we consider a measure for probability. And we call it P. Like P of, for example, probability of event A is equal to 0.5. Something like that. Like rolling a die. Probability of being head or tail is half if the coin is a normal coin. Sometimes it's not. So it's half. So we define a probability a measure on sample space with this axiom. This is the axioms that is considered Kolmogorov axioms or probability axioms. The first rule or axiom that we have is non-negativity. Probability cannot be negative. It's always positive. That's the first axiom. The second one is normalization. Normalization means it needs to be between 0 and 1. It needs to be between 0 and 1. Or probability of a sample space is always 1. So like probability of sample space is like all the universal set. So that the probability of this is 1. And for example, this is one event A. The probability of this event, for example, P of A, is 0.4, for example. Something like that. So we gave numbers to those events. We gave numbers. When you play with numbers, you are simulating, kind of. You are modeling. And this is what we need to do. As an engineer, our work is modeling. We always model. We model things. We want to model reality. We want to model things. Why we model things? Because what? Why we model things as an engineer? What? What?
Makes it easier to explain things.
Explain things, right? Yes. It's easier to explain it. It's easier to predict it. So we model it. So with numbers, we can, OK, what is the third axiom? The third axiom is additivity. OK, so let I clean this. So additivity means if two events are mutually exclusive, it means it's not possible to happen at the same time. If two events cannot happen at the same time, you can say probability of A or B is P of A plus P of B. So this addition is kind of math. We brought math inside probability. Before 1900, we didn't consider math. We didn't consider numbers for probability. We just considered gambling, tail, and head, or coin, and whatever. In physics, probably we use that, but not as a math, just as something random. So these three axioms are very important for us to understand how probability works. We can assign numbers to them. And when we put capital P, means the probability of that event. If it's like A is event, omega is a notation for all set or sample space, like a universal. OK, so this is the axioms of probability. Example. OK, imagine we have a robot that is moving. With these examples, I want to make it more tangible for you guys. OK, we have a robot that is moving. So let us see. This is a robot. However, we have different type of robots. Some robot can just move, they have a steering wheel, some of them, we don't, OK, so imagine this robot can go left and right. So this way and this way. This is left. This is right. In my side, maybe in your side is vice versa, but you understand that. And we called going to left A, and going to right B. This is the event. So, okay, so this event can happen. First of all, can they happen at the same time? Can we go right and left together, like at the same time? No. So they are mutually exclusive. We can't happen at the same time. So that's a good point. So if you want to consider what is the probability of going left or right, we can write that as an addition. Probability of left plus probability of right. Okay, so that's one example. Another example for a fair die, again, when you have a die, I love to draw in die. Okay, so the probability of happening, for example, 6 coming is 1 over 6, because when you drop it, 6 actually possibilities can happen. So probability of being 6 is 1 over 6, probability of 5 is 1 over 6, probability of, they are all equal. Okay? So in general, probability of I is 1 over 6. I means I can be 1 to 6, because these 6 events can happen. 6 outcomes can happen. Okay? So what is sample space? Sample space is all outcomes. So when the outcomes are 1 to 6, so this is sample space. And what is probability of even numbers? We have 3 even numbers, 2, 4, and 6. And because they are mutually exclusive, we can write them 1 over 6 plus 1 over 6 plus 1 over 6, 1 over 2. So that's actually we are using the third axiom for computing this. Because this is additive axiom, we can, when 2 events are mutually exclusive, P of A or B is P of A plus P of B. Okay, this is what we use. Any question about that? It's very simple so far. It's going to be simple. As far as we solve things with examples and tangible things, you can see this is not difficult. I also had in my undergrad this course, and it was really difficult for me. And for masters, again, not for masters, but for grad school, for PhD actually it was, but I had a course called estimation. And in that course, we were seeing how practically we use these rules and math and probability. And that time I learned them much better. And I realized, oh my God, we can use them in real world. So that's why I try to bring very tangible hand-on exams in the class to explain for you guys how this math can be used practically. Okay, so that was example. Let's do, this is another one. If you want to use odd numbers also the same. And probability of okay. If we consider event A is even numbers and B is odd numbers, Pi or B is all the actually sample space, and probability of sample space is 1. Based off second axiom. This is the second axiom. Because in second axiom, we said that is normalization. Second axiom is, okay, normalize. It means it's between 0 and 1. So the maximum should be 1, and the maximum is for sample space. All the sample, all the universe is 1, and we just choose part of that. That's a very important part. Sometimes we compute probability, and we didn't consider this normalization. We always need to normalize. We say, okay, the likelihood of this event is that, the likelihood of this event is that. But when it's likelihood, and you want to change it to probability, you need to normalize it. You need to consider all these events that are happening, for example, rain, weather. So, okay, possibility of, for example, rain is 30%, possibility of cloudy is like 60%, possibility of snow is this much, possibility of sunny is this much. So at the end, you need to add them together and need to be 1. If you not make it 1, it's not probability. So that's important. That's called normalization. Normalization is a very important part. In machine learning, you have it as well. So because machine learning is all based off that. So you normalize it. Normalization is very important to make the bandwidth between 0 and 1. And we can't have negative. We don't have negative. We need to normalize it and additive. These 3 rules are very important. If you want to have probability, you need to consider these 3 rules. We call them axioms. Good. Let's do one quick activity. Can you try to do this eye clicker? I want to just check it, see you are able to. At the same time, I try to activate that here. Let's see. I still didn't define it, so let's see. Time. Okay, start the class. Okay, I put it. Multiple choice. I first try to question 1. Wait a second. Yes, okay, start. Okay. Okay, let's do the question 1. Okay, 4 people, 6 people already did. What? Are you doing by chance? Oh, okay. So let's show you the result.
Makes sense. So. All independent.
Don't get fooled. That's not right. A is right. So the sample space cannot repeat it, you know.
Why?
Sample space is just red, green, and blue. So the first one is correct. A is correct. Okay, so let's do the second one, okay? Oh, you fixed it? Okay, let's do it again. Like here, I changed that. Okay, do it again for the second one. What is the probability of drawing a green or red? So this is what we have. We have 2 green. We have 3 red. And we have 5 blue.
I see it.
Okay.
Eye flicker.
Oh, is it covering that? Okay. I think you all did that right. Okay. Move it here. So, probability of, I think you did all right. Probability of being red is 3 over 10, because we have 10 in overall. Like probability of red or green is equal to 3 over 10 plus 2 over 10. That is 5 over 10. That is C. Did you select C? Yes, of course. Good. Okay, it was a good test. See how it works. Any question about this? Oh, how many people applied? Okay. Okay. Good. Okay. Another example. Another example is, again, robotic activity. In this example, we have a robot, a mobile robot, at a junction. So this robot can move in a different direction, can go forward, can go left, can go right. Yeah, this is left and right in my view. And stop, stay in the same place, stop. So this is all situation that happen in this junction. So it's, for example, in a grid and can go right, left. Most of the robot cannot do like this. They need to turn. They have a steering wheel. They have another wheel here, and you need to have an angle and angular velocity. Is more complicated than this. But we make it very simple. We say, yes, this robot is possible. Some robot can. Some robot, like for example, it can be a drone can. Or some robot have a very specific wheels that can move in any direction. They have a name. Anyway, so in this robot we can, and we said we have 4 possible move, forward, left, right, and a stop. And we want to see what? And at the probability of each one given. Like if you go forward, probability is 0.4, left, right, and a stop. First of all, if you add them together, need to be 1. Is it true? Yes. It's add up to 1. So that's the second axiom. We need to consider that all the time. What is the sample space? Okay, so what is the sample space? All possible, outcomes that happen. Forward, left, right, and stop is sample space. Oh, I didn't. So the sample space in this case gonna be forward, left, right, and stop. What is the probability that robot changes heading? Changes heading. Okay, if it's go directly forward, we are not changing the heading. Left and right, we change the heading. So we want to see what is the probability of left or right. So because they are mutually exclusive, we can't do that at the same time. It's equal to P of left plus P of right. And if we add them together, 0.2 plus 0.3 is 0.5. Okay? Any question? Simple, not difficult. But maybe you ask me a little deeper. Does the robot need probability to go this, that? I don't know. Yes, actually, why not? We can say, like, imagine if the robot wants to go left or right, need to expend more power, for example. Something like that. And that's important for us. So that's why we consider some probability, that probability coming from the use of power, like a battery, for example, level or something like that. Yeah, we can define problems like that all the time. But this was just a sample. We wanted to see if you have different outcomes. First of all, what is the all of those outcomes coming in the sample space, and how we can do actually additive add to probability if they are mutually exclusive. Okay, so let's do another example. Okay, this is for home. I want you to do it at home. It's a practice, and we can do that next class. Okay, so I'm just going to pass. It's about target tracking. I'm going to explain a little bit what is the problem. So we have two targets. When we are talking about target, for example, imagine two drones. You have one drone here and another drone here. This is drone, imagine. Okay? They are target. And we have a, using sonar sensor. Yes, and we have a radar or sonar or some sensors to detect their position. So we have, for example, some device to actually find the position of them. That's called tracking. Tracking means estimating the position of targets. Target can be everything. Can be car, can be pedestrian, whatever. Can be drone, airplane, anything. That is tracking. Tracking means estimating the position of target. That's called target. When you find the position, and it's all uncertain, it's not certain. You can't find it 100%. You always have some tolerance. That's why when you find that, you say, okay, it's in this position, but with this uncertainty around it, with this mean and covariance. That's why in this class we can solve this kind of problem. And this one, for example, detecting this is harder. So it means, so for example, here is some cloudy areas. So it is behind a tree or something. You can see that 100%. So the those threshold or covariance or variance is bigger. So when you say is this, say, okay, this much noise you have, this much uncertainty you have, this much, for example, a meter uncertainty. Compared to that, that is a half a meter, for example. Okay, in this example, we want to measure some, actually we want to find sample space, and we want to find some probability. Do it at home. I just wanted to explain what is the problem to do it easier. Okay, another thing that I should mention that before going to next slide is false alarm. In tracking, sometimes you detect target, but it's not target. It's false alarm. False alarm, sometimes called actually outliers. Outliers or false alarm. False alarm is different than noise. Noise is different than false alarm. Noise is around the target, but false alarm is something else. You were thinking that's a drone, but it was, for example, I don't know, a bird. This happened. in these examples. So false alarm is very important to consider. So we consider false alarm as one of the events that happening. Okay, good. But I just wanted to explain that before going to next slide. Okay, do another example before going to another topic. And that's very important example when you have a sample space that is not finite. You have a sample space that's going to infinity. This is one of the examples that we need to consider. Imagine we have an infinite sample space. So in examples that we did, mostly we had finite sample space. Like in robotics, we can go right, left, stop, right, forward. Or, for example, in die, for example, 1 to 6. In coin, head and tail is finite. But what about is not finite? It's going to infinity. How we can deal with that? Can we define that as a probability as well? Because if we want to model things in similar to the math, in math we have numbers that going to infinity. Sometimes minus infinity, sometimes plus infinity, sometimes discrete, like 1, 2, 3, sometimes real numbers. So in that case, how we can deal with probability? First, we need to check if we have a sample space like that. Is that probability at all? Can we define the axioms? Okay, what about the first axiom? First axiom was non-negative. Okay, that can be non-negative. That's okay. That's okay. That's fine. Axiom 2 is a little complicated, so we're going to talk about axiom 2 later. Axiom 2 is to add up to 1. Okay, we're going to talk about that later. First, go to axiom 3. Can we make it kind of that we consider additivity? Additivity is also when we say, okay, two outcomes are mutually exclusive, it cannot happen at the same time, we are adding the probability. That's also possible because it doesn't matter you go to infinity or not. But the second axiom is a little tricky, normalization. Normalization means if we add them together, they need to be 1. How we can add something from 1 to infinity and become 1? Is it possible? So how we can add, imagine we consider similar probability to each of them, like the one that we did with rolling a die, or the one that we did with tossing a coin. We consider equal. Do you remember in rolling a die, we said sample space is 1, 2 to 6, and probability of I is 1 over 6. It's equal. Doesn't matter what is I. If it's 1, if it's 2, if it's 6, it still is 1 over 6. They are equal. They are kind of symmetric. They're kind of symmetric. Okay? So let's show you in a different way. So imagine this is event I, and this is probability of I. So we consider if it's 1, 2, 3, 4, 5, 6. This is always 1 over 6. If we add them together, 1 over 6 plus 1 over 6, 6 times is going to be 1. This is the diagram that we draw. Probability based off events that happening. But in this case, how this can be 1? This is infinity. Imagine you consider anything, 1 over n equally. And 1 over n, but n is infinity, n going to infinity. So 1 over n plus 1 over infinity plus 1 over infinity. It's not possible to be 1. How we can make it 1? We need to kind of move from symmetric to non-symmetric case. You know, you need to kind of define a function for that. Later we call that function distribution. Here is a place that distribution coming. Distribution is a function that define the probability based off sample, based off those events. So let I clean this up. We need to define distribution. Distribution is the function that telling us what is probability of event n. Imagine we consider that 1 over 2 power n. In that case, if we add them together, it's going to be 1. Why? OK, let's do it. P of omega, if n is 1 over 2. If n is 2, 1 over, this is n, 1 and 2, 1 over 4, 1 over 8, and so forth. Infinity. OK? So how we can prove this is 1? It's a series. Probably you had it in different classes. I don't know. Can you prove it? You try to prove it. Why this is 1?
Oh, yeah, no, yeah, that's a geometric series. Is that you could
Geometric series. Exactly. Very good. Yes, that's a geometric series. So to solve that, you just need to factorize 1 over 2. So we can say, OK, that's an x that we want to compute. Imagine this is x. OK? It's geometric, exactly. Very good point. We can say this is 1 over 2. 1 plus, when we factorize 1 over 2 from it, it's going to be 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over infinity. So this is also x. So this equation becomes x is equal to 1 over 2, 1 plus x. And x can be computed based off that. I'm going to write it here. I hope you don't mix it up. Let's clean this. It's going to be 2x is equal to 1 minus x. And x is 1. Oh, plus. Proved. It's 1. So that means we can have. So what is the takeaway? So the takeaway is probability is about measuring things. It's not always symmetric. It's not always equal. You don't give equal actually probability to all outcomes. Sometimes to some of them more, give them more privilege, sometimes less. And here happen. When n is less, you give more probability. When n gets bigger and bigger, you shrink that probability lower and lower and lower. When to add them together is going to be still 1. So the axiom 2 going to get proved. So, but to do that, we also define something new that's called distribution. So the distribution is a function. Is a function that defines the probability based off the n. If n is 1, is, for example, 1 over 2. If n is 10, 1 over 2 power 10. And when it's infinity, 1 over 2 power infinity. When add them together, become 1. OK, we're going to talk about that more. But I just wanted to just get general. OK, let's go for another. Examples. Conditional probability. OK. Another important thing that we need to consider is conditional probability. What about if you have some prior information, like somebody tell you, OK, you're playing card, and somebody tell you, OK, that's face card. So you know that is face card. And now you want to find probability of something. So playing card is actually a very good example. When you play with card, so normally you have 52 cards. So, for example, if you say, OK, what is the probability of you are selecting one of these cards between 52? What is the probability of being, for example, king of diamond? You tell me. What is the probability? We choose one thing. We shuffled that many times. And you're going to select one. And what is the probability that the king of diamond? 1 over 52. Perfect. 1 over 52. But if I tell you, imagine the one that you are selecting is a face card. OK? I give you this information that this pack is all face. Now what is the probability of having king? So how many face we have? 12, right?
Are you counting ace?
We have 12 face. For each one, am I right? We have 12 face. Yes, we have 12 face. So if we know it's 12, instead of having 52, right now we have 12. So it's 1 over 12. So the probability is getting higher. I'm not sure. Let's check. Yes, I think. So probability of being king is, yes, 12. I just was, because we have 4 color, and we have 4, so it's going to be 12. Oh, 3, sorry. We have 3 colors, and we have 4 different, so it's going to be 12 cards. Like face cards are going to be 12. And each one jack, queen, or king. And you have 4 different. So it's going to be 12. Is that right? Good. I'm not good player. I'm not good card player. So that's called conditional probability. How we show that? We say, OK, what is probability of king if we know given face card? It's called given. When we put a line like that, we say given. What is the probability of being king given face time, a face card? So in this case, it becomes 1 over 12. In this case was 1 over 52. I don't know what number it's going to be. And in that case, it's going to be just 1 over 12. OK? But how mathematically can define that? Conditional probability has a formula. And this is the formula that's coming. And this formula is going to make so many other things later we can get from that. So probability of A given B is probability of A and B. Probability of A and B. What is and means? Probability of one event and two events. When we say and means together. Probability of A and B means probability A and B happened together. So we also, sometimes we write like that. P A and B is P A comma B. It means they do that together. So that's a probability of A and B. When we say two events are mutually exclusive, means P A and B is 0. Because we say, oh, they can't happen at the same time. So probability of happening at the same time is 0. Okay, so this just was extra. I just wanted to mention. Okay, so this is the formula for probability of A given B. So probability of, I want to just explain it. I'm going to write it again. A given B is equal to P and B happening at the same time divided by P of B, because we already know B. We want to take that out. We have enough information about B. So this is going to help to probability become higher, because we have some information about that event. If we have some information, extra information, that's called prior information sometimes. Prior information. In P of A given B, B is something that is given. Somebody gave you this information. So you know that. Okay? It's very important because so many actually prediction coming from this. So when you want to predict something, this prediction coming from some prior information, isn't it? So you want to, for example, predict the position of the robot. Very tangible example. So you want to find probability of X given what? Given Z. Z is the measurements. Z is the measurements. We want to see what is the probability of, what is the X given those measurements. Those measurements like sensors. Robot has sensors. Can find, for example, GPS, for example. GPS is directly give you the position. Or maybe just IR give you distance to walls. And other things, some robot, they have also some sensors to measure their speed, their velocity, their acceleration, their, like dynamic. So you can estimate X. X is the position that you want to find. Later on, we can see this kind of problem called actually inference. Inference means finding X based off this probability. This is called inference. We can see that later, don't we? But I want to say how important is conditional probability. So the conditional probability has that formula. Let I clean this up. Okay, so this formula showing actually how we can find conditional probability based off probability of A and B divided by B. Okay. Okay, so it means we have some information. We have, already happened. So how we can actually think about A. Let's have example. Again, playing the card is a good example. The things that we did in the last slide, we want to do that here with the formula. Okay? So the same things. We want to find probability of king if it's already face card. We already know it's face card. We have 12. And you can directly compute that. But let's do it with that formula to see if they are equal. What is the probability of being king and face? Okay. So being king and face, because we have 4 king. So it's 4 over 52. What is probability of face? We have 12 face in all of 54, so it's 12 over 54. If we divide them together, it's going to be 1 over same response, the same number, but different method. In the other one, we just intuitively, we just think about that, okay, it's 12, so 1 over 12. That actually 4 over 12, 1 over 3. Okay, that's called conditional probability. We're going to talk about that a lot and a lot. So if you didn't get that 100%, still don't worry about that. But if you have any question, let me know to go to the next part. Another important part that we need to know is multiplication rule. Multiplication rule is kind of computing probability of multiple events that happening at the same time. This is sometimes very important when you want to compute, for example, P of A and B and C and D. You know, you have multiple events that are happening at the same time. They are happening at the same time. When we are saying two events happening at the same time, doesn't mean that they are dependent. They might be, but it's not always they are dependent. You know, probability of two events that are happening at the same time is not always showing that they are dependent. Sometimes they are independent. We can talk about that. Are we done? Oh, I think so, yeah. So we, okay, so because I don't, we start at 9:30, am I right? Okay, so we can have 10.
An hour and 15 minutes.
1 hour, okay. So right now we are 1 hour and 15. You're right, yeah? Okay, good. Okay, so it doesn't matter. We can talk about that next class. I'm still confusing with the other. Okay.
Did you see that?
Yeah, Jeff is trying to offload it on your.
Let's talk about next class because I need to talk a lot about that.
Not MA.
Of course. I will. Thank you so much. Yes, of course.
The exact same class I'm going to lose my mind.
Yes.
This mostly means that I could have graduated next year.
That's no fucking blast.
One class off.
Use Yes.
Then after they play.
I played a good
Wait a second, I just...
last year we were in the team.
Yeah, so.
And what is